Picture a time before time, a universe so dark, so empty, that not a single star flickered in the endless void. This was the cosmic dawn, the moment when everything changed. For billions of years after the Big Bang, the cosmos was a shadowy expanse, filled only with swirling gases and silence. Then, slowly, impossibly, the first sparks of light began to pierce the darkness. These weren't just stars, they were the architects of everything we know today, the first builders of galaxies, the creators of the very elements that make up you and me. And yet, despite their monumental role, we know almost nothing about them. How did they form? What did they look like? Why did they ignite when they did? These are just a few of the 25 mysteries that still haunt scientists studying the cosmic dawn era, that elusive chapter when the universe woke up and began to shine. Think about this for a second. Every star, every planet, every speck of dust in the cosmos traces its origins back to that pivotal era. The cosmic dawn wasn't just the birth of light, it was the birth of possibility. But here's the thing, the deeper we look into this ancient epoch, the more questions we uncover. Some of these puzzles defy our best theories, while others hint at forces and phenomena we can't even begin to explain. Why did some regions of the early universe light up with stars while others remained shrouded in darkness? How did the first galaxies assemble themselves out of chaos? And what strange, invisible players, dark matter, primordial black holes, or something even more exotic, pulled the strings behind the scenes? The cosmic dawn isn't just a distant memory, it's a cosmic crime scene, and we're the detectives piecing together clues that have been scattered across 13.8 billion years. This is where the story gets thrilling, because right now, with cutting-edge telescopes peering back to the edge of time itself, we're on the verge of breakthroughs that could rewrite everything we thought we knew. The cosmic dawn era is no longer just a faint whisper from the past, it's a living mystery, one that's begging to be solved, and that's exactly what we're about to do. Over the course of this journey, we'll unravel 25 of the most jaw-dropping, head-scratching enigmas from this primordial age. From the bizarre behavior of the first supermassive black holes to the ghostly signals left behind by the universe's very first light, each mystery is a doorway into the unknown. So buckle up, we're about to travel back to the dawn of everything, and trust me, what we find there will change the way you see the cosmos forever. The first stars were unlike anything we see in the night sky today. Born from the raw, unpolluted gases of the early universe, these cosmic pioneers, known as Population 3 stars, were true titans, blazing with a ferocity we can hardly comprehend. And yet, despite their monumental importance, we've never laid eyes on one. Not a single trace remains in our telescopes. So where did they go? The answer lies in their extraordinary lives and explosive deaths. These stars didn't form like modern ones. Without heavy elements to cool the collapsing gas clouds, they grew monstrous, some reaching masses hundreds of times that of our Sun. Imagine a furnace so powerful it could outshine entire galaxies, burning bright and fast, destined to live only a few million years before collapsing in cataclysmic supernova or even vanishing into black holes. That's the fate of the universe's first stars, brilliant, brief, and gone without a trace. Their ashes became the building blocks for everything that followed, seeding the cosmos with the first heavy elements, paving the way for smaller, longer-lived stars like our Sun. But here's the twist, we might not be looking in the right place. The light from these ancient giants has been stretched by the expansion of the universe, shifted into infrared wavelengths invisible to our eyes. Even our best telescopes struggle to peer that far back. Some theorists suggest these stars might still be hiding in plain sight, masquerading as distant galaxies or lurking in the shadows of supermassive black holes. Others believe their remnants could be scattered across the cosmos, disguised as faint, metal-poor stars in our own galaxy. It's a cosmic game of hide and seek spanning billions of years. What makes this mystery even more tantalizing is what these stars left behind. Their deaths forged the first heavy elements: carbon, oxygen, iron, the very ingredients of planets and life. Without them, the universe would still be a featureless sea of hydrogen and helium. So while we may never directly observe a population 3-star, their legacy is written in the atoms of our bodies, the rocks beneath our feet, and the glittering tapestry of galaxies around us. They were the universe's first alchemists, and we're living proof of their work. The hunt for their origins isn't just about solving an astronomical puzzle, it's about uncovering our own cosmic ancestry. If the cosmic dawn was a grand theater, dark matter was supposed to be its invisible stage, holding everything together while the first stars took center light. But something's wrong with this picture. According to our most sophisticated simulations, dark matter should have clumped into dense halos during this era, creating gravitational scaffolds for the earliest galaxies to form. Yet when we peer back with telescopes like the James Webb, what we see doesn't match the script. The galaxies are there, but their dark matter arrangements look off. Some regions that should be crowded with matter appear startlingly empty, while others are denser than physics predicts. It's as if the universe's hidden architect left behind half-finished blueprints. Take the puzzling case of ancient ultra-faint galaxies. These cosmic relics surviving from near the dawn of time should be drowning in dark matter, but many have barely any at all. Meanwhile, certain massive early galaxies formed with such speed and precision that they'd require dark matter behaving in ways we've never observed. The discrepancies are so glaring that some scientists are questioning whether we've misunderstood dark matter's fundamental nature. Could it interact with itself through unknown forces? Might it have been heated up by primordial explosions, scattering it unevenly? Or perhaps, and this is where things get really wild, what we call dark matter isn't one substance but multiple, with some components decaying or transforming over cosmic time. The implications ripple far beyond early galaxy formation. If dark matter didn't play by the rules during the cosmic dawn, our entire understanding of how structure emerges in the universe could need rewriting. Modern galaxies, including our Milky Way, likely inherited their dark matter distributions from this chaotic period. Those initial irregularities might explain why dark matter seems to cluster differently in various parts of the cosmos today. Even more tantalizing, this mismatch could hint at cracks in our core theories of gravity or spacetime itself. What's clear is that the cosmic dawn isn't just revealing dark matter's secrets, it's exposing how much we still don't know. Every anomalous galaxy is a clue, and with new observatories like the Roman Space Telescope joining the hunt, we may finally glimpse the shadowy physics that shaped the universe's first structures. One thing's certain, the dark matter story is far stranger than we imagined. Imagine the universe as a vast, murky fog, so thick that light couldn't travel far before being swallowed by the darkness. That's how things stood for hundreds of millions of years after the cosmic dawn, until something extraordinary happened: the fog lifted. This was reionization, the universe's great unveiling, when neutral hydrogen gas, the remnants of the Big Bang, was torn apart into its charged components, transforming space into the transparent expanse we know today. But here's the puzzle. We still don't know exactly what caused it or why it unfolded over hundreds of millions of years when our best calculations suggest it should have happened in a flash. The leading suspects are the first stars and galaxies, their intense ultraviolet radiation blasting away the hydrogen fog like cosmic spotlights. But there's a problem. When we tally up the light from known early galaxies, there simply doesn't seem to be enough to do the job. That's where quasars enter the scene, supermassive black holes at the hearts of galaxies, devouring matter and spewing out enough energy to outshine entire universes. These cosmic lighthouses could have played a major role, but they're rare in the early universe. So did stars or black holes dominate, or was there another, even more exotic player we haven't accounted for? The mystery deepens when we look at the timeline. Reionization didn't happen uniformly. Some regions cleared early, others stubbornly held onto their fog. This patchwork process suggests a chaotic interplay of forces, with bursts of star formation or sudden quasar activity creating bubbles of transparency that slowly merge. Even stranger, recent observations hint that reionization might have started earlier and ended later than we thought, overlapping with the formation of the very first galaxies in ways we don't yet understand. What makes this puzzle so critical is that it's not just about ancient history. The way reionization unfolded shaped the entire future of the cosmos, determining how galaxies could grow and how light could travel freely across billions of years. It's written into the very fabric of the cosmic microwave background, the afterglow of the Big Bang, where subtle patterns reveal the fingerprints of those first ionizing photons. And with new telescopes like the James Webb Space Telescope probing these primordial epochs, we're closer than ever to catching the culprits in the act, whether they're brilliant young stars, voracious black holes, or something even more unexpected. The reionization puzzle isn't just a gap in our knowledge, it's a window into the universe's most transformative moment. There's something deeply unsettling about the early universe. It refuses to follow the rules. Take those first galaxies, for instance. When the James Webb Space Telescope began peering back toward the cosmic dawn, astronomers expected to see faint, fledgling systems, barely more than smudges of light. Instead, they were blindsided by galaxies shining with impossible brilliance, some glowing as brightly as modern galaxies 100 times their size. It's like digging up a prehistoric cave and finding a neon sign inside. These cosmic overachievers shouldn't exist, at least not according to our best models of galaxy formation. So what's really going on? One possibility is that star formation in the early universe was a far more violent affair than we imagined. Today, stars are born at a leisurely pace, with galaxies like ours producing perhaps a few suns each year. But back then, conditions may have been ripe for explosive bursts of star birth, with entire generations igniting in fireworks of creation. Imagine nurseries not just making stars, but forging them by the millions, cramming stellar lifetimes into mere cosmic moments. If true, these galaxies wouldn't just be bright, they'd be temporary infernos, burning through their fuel so fast that their brilliance was fleeting. That could explain why we don't see their modern counterparts. They literally burned out. But there's another, even more radical idea lurking in the shadows. What if the light we're seeing isn't just from stars? Some theorists suggest these galaxies might harbor supermassive black holes growing at breakneck speeds, their accretion disks blazing with enough energy to outshine every star in their host galaxies combined. Normally, black holes this big take billions of years to form, yet here they are, fully grown when the universe was barely a toddler. Their existence throws our entire timeline of cosmic evolution into question. Did some black holes form directly from collapsing gas clouds in the early universe, skipping the star stage entirely? Or is there some exotic mechanism, primordial black holes, cosmic strings, or even relics from a pre-Big Bang era that gave them a head start? The plot thickens when we consider the role of dark matter. If it clumped differently in the early universe, creating denser gravitational wells than predicted, it could have funneled gas into galaxies at outrageous rates, supercharging both star formation and black hole growth. Alternatively, our understanding of stellar physics itself might need an overhaul. Early stars could have operated under different rules, burning hotter and brighter due to their pure hydrogen-helium composition. Or perhaps the light we're seeing has been magnified by cosmic lenses, gravitational distortions from invisible mass warping space along our line of sight. Whatever the explanation, these dazzling early galaxies are forcing us to rewrite the cosmic playbook. Each anomalous point of light is a clue, a whisper from an era when the universe played by different rules. And with every new observation, we're not just solving a puzzle, we're uncovering a stranger, more dynamic cosmic dawn than anyone dared imagine. The universe had all the ingredients for life almost from the very beginning. Within a few 100 million years of the cosmic dawn, the first stars forged heavy elements, planets coalesced from their ashes, and liquid water could have pooled on ancient worlds. By all accounts, alien civilizations might have arisen when the universe was less than 10% of its current age. So where is everybody? This eerie silence is more than just a puzzle. It's a haunting cosmic riddle wrapped in the mystery of time itself. Consider the staggering head start early civilizations would have had. Planets orbiting population 3 stars might have hosted life billions of years before Earth even existed. Imagine a technological species arising when the universe was a mere 1 or 2 billion years old. By now, they'd have had 10 billion years to expand, explore, or leave detectable traces across the cosmos. And yet our telescopes hear nothing. No signals, no megastructures, not even a whisper of activity. It's as if the early universe was a stage set for a play that never began. One chilling possibility is that life in the cosmic dawn was doomed from the start. Those first stars were volatile giants, prone to cataclysmic supernova and lethal gamma-ray bursts. A single stellar explosion could have sterilized entire galactic neighborhoods, snuffing out any fledgling civilizations before they could spread. Even if life clung on, the extreme ultraviolet radiation bathing early planets might have made complex chemistry impossible. The universe's first habitable worlds could have been cosmic shooting ranges, with life constantly reset by apocalyptic events. But there's another, more unsettling angle. What if early civilizations did flourish, just not in ways we'd recognize? Our search for extraterrestrials assumes they'd communicate via radio waves or build visible structures. Yet a species evolving in the primordial universe might have developed entirely different technologies, perhaps harnessing dark matter or tapping into quantum fields we can't yet detect. Their artifacts could be all around us, hidden in plain sight, written into the very fabric of space-time. The Fermi paradox takes on a new dimension when viewed through the lens of deep time. If civilizations rose and fell during the cosmic dawn, their ruins would now be impossibly distant, their signals stretched into undetectable whispers by the expansion of the universe. We might be like archaeologists sifting through an ancient desert, unaware that the sands around us hold the remnants of a forgotten empire. Or perhaps the answer is even more profound, that the universe's first life forms transcended physical form entirely, leaving our material cosmos behind for realms we can't yet fathom. This isn't just speculation about aliens, it's a mirror held up to our own future. If early civilizations consistently vanish or transform beyond recognition, what does that suggest about humanity's trajectory? The silence of the cosmic dawn might be the universe's oldest cautionary tale, or its most tantalizing invitation to look deeper. Either way, the absence of evidence is becoming one of the most compelling mysteries of all. Supermassive black holes didn't just appear in the early universe. They arrived fully formed, like uninvited giants at the cosmic dawn party. These behemoths, some weighing billions of times the mass of our sun, are found in galaxies when the universe was less than a tenth of its current age. That's the equivalent of discovering a skyscraper in the middle of the Stone Age. How they grew so big, so fast, is one of the most perplexing riddles of the cosmic dawn, and the answers might rewrite our understanding of black hole physics itself. For decades, scientists assumed supermassive black holes grew slowly, feasting on gas and stars over billions of years. But that timeline shatters when we look at quasars, luminous monsters powered by these black holes shining brightly when the universe was barely 700 million years old. To reach such staggering masses in that blink of cosmic time, they'd need to consume matter at rates defying known physics, swallowing the equivalent of a sun every single day without pause. That's not just gluttonous, it's theoretically impossible under standard models. Something else must have given them a head start. Enter the radical idea of direct collapse black holes. Picture this: in the primordial universe, before stars polluted space with heavy elements, vast clouds of pure hydrogen gas could have collapsed under their own weight, not into stars, but straight into black holes thousands of times more massive than our Sun. These seeds wouldn't need to grow slowly. They'd be born enormous, skipping the awkward stellar phase entirely. It's like a baby arriving the size of a sumo wrestler, ready to dominate from day one. But there's a catch. For this to work, conditions had to be just right. No nearby supernova stirring the gas, no pesky atoms heavier than helium cooling the mix. Even a single population 3-star dying too close could spoil the entire process. That makes these direct collapse events incredibly rare, yet somehow common enough to explain the swarms of early quasars we observe. It's a cosmic Goldilocks problem. Too much turbulence and you get stars, too little and you get a black hole. The universe, it seems, walked this razor's edge perfectly. Not everyone's convinced, though. Alternative theories suggest these black holes might have grown from dense clusters of early stars, their remnants merging into something monstrous. Or perhaps they fed on dark matter itself, tapping into hidden reservoirs of mass we can't yet see. Some even speculate about primordial black holes, leftover wrinkles from the Big Bang that could have jump-started the whole process. The wildest ideas involve cosmic strings or extra dimensions funneling energy into these voids faster than nature normally allows. What's undeniable is that these early black holes didn't just sit quietly, they shaped the cosmos around them. Their intense radiation may have catalyzed galaxy formation, their outflows carving bubbles in the intergalactic medium. Some theorists argue they acted as cosmic regulators, their growth spurts shutting down star formation in their host galaxies, creating the bizarre mismatch between galaxy and black hole sizes we still see today. The mystery isn't just academic. If supermassive black holes really did form through unknown mechanisms, it implies our universe holds shortcuts, processes that bypass the plodding pace of conventional physics. Discovering these rules could reveal entirely new chapters in how structure emerges from chaos. And with telescopes like the James Webb and upcoming gravitational wave detectors, we're closer than ever to catching these cosmic overachievers in the act. One thing's certain, the early universe didn't play by the rules we wrote, and that's what makes the hunt so thrilling. Something was lurking in the cosmic shadows, something we almost missed entirely. The early universe should have been a sea of neutral hydrogen, spread out evenly like fog across a vast, silent ocean. But when radio telescopes finally tuned into the cosmic dawn's faint whispers, they revealed a startling truth: this hydrogen wasn't smooth at all. It clumped in strange, uneven patterns, with dense patches scattered between enormous voids like a sponge left to dry under the heat of the first starlight. This wasn't just unexpected, it upended our most fundamental ideas about how structure emerged after the Big Bang. Take the groundbreaking observations from arrays like the Murchison Widefield Array in Australia. By detecting subtle ripples in the hydrogen fog, the echoes of 21-centimeter radiation stretching back over 13 billion years, they've mapped a landscape more chaotic than anyone predicted. Some regions were nearly empty, as if scooped out by an invisible hand. Others bore thick knots of gas that defied gravity's usual rules, the strangest part. These irregularities appeared too early, too pronounced to be the work of stars or galaxies alone. Something else, something dark and enigmatic, was pulling the strings. Dark matter is the prime suspect, but even that doesn't fully solve the puzzle. According to simulations, dark matter's gravitational tug should have created a subtler, more uniform web of hydrogen variations. Instead, we're seeing extreme contrasts, hotspots and cold spots that resemble the aftermath of cosmic explosions. Could supernova from the first stars have blasted cavities in the hydrogen fog? Possibly, but the scale is all wrong. These voids span millions of light years, far larger than any single stellar explosion could carve. Here's where the mystery twists. Some theorists propose that exotic physics, like interactions between dark matter and radiation, might have sculpted these hydrogen deserts. Others wonder if primordial magnetic fields, woven into space itself during the Big Bang, stirred the gas into unexpected shapes. Then there's the wild card, quantum fluctuations from the universe's first moments, amplified beyond all prediction, leaving ghostly fingerprints in the hydrogen's distribution. The stakes are higher than they seem. Hydrogen wasn't just a passive backdrop. Its uneven layout directly influenced where stars could ignite and galaxies could grow. Those early patches of dense gas became stellar nurseries, while the voids remained barren for eons. In other words, the universe's fate hinged on a cosmic dice roll we still don't understand. Now, with next-generation radio telescopes like the Square Kilometre Array coming online, we're on the verge of decoding this ancient hydrogen puzzle. Every distortion in the signal, every unexpected ripple, is a clue to forces we've yet to name, and buried in those patterns might be answers to the biggest question of all: why does our universe look this way and not some other? Black holes come in two familiar sizes, the stellar mass ones, born from collapsing stars, and the supermassive monsters anchoring galactic centers. But between these extremes lies a ghostly gap, the realm of intermediate mass black holes, those elusive middleweights that should bridge the cosmic divide. And here's the frustrating part: when we turn our telescopes toward the cosmic dawn, they're nowhere to be found. It's like searching for a missing link in evolution, only to find the fossil record stubbornly blank. These intermediate black holes, ranging from a few hundred to a few 100,000 solar masses, should be everywhere. They're the logical stepping stones, the cosmic glue connecting tiny stellar remnants to the supermassive behemoths. Theory predicts they'd form through runaway collisions in dense star clusters or as seeds for the first quasars. Yet despite decades of hunting, concrete evidence remains maddeningly scarce. Even the James Webb Space Telescope, with its unprecedented infrared vision, has turned up empty-handed in the early universe, so where are they hiding? One possibility is that these black holes are masters of disguise. Unlike their supermassive cousins, which announce their presence with brilliant accretion disks, intermediate black holes might lurk in quiet obscurity. Without enough nearby gas to feast on, they'd emit little radiation, effectively invisible to our telescopes. Imagine a ghost town where the only way to spot the mayor is if they're shouting, but if they stay silent, the place seems abandoned. That could be the case here. Another clue lies in their formation. Stellar mass black holes grow by swallowing gas or merging with others, but in the early universe's sparse environment, those meals might have been too few and far between. Picture a sapling struggling in barren soil. It never reaches its full potential. Similarly, these intermediate black holes could have starved before reaching detectable sizes, stunted by the very epoch they were born into. Then there's the explosive alternative. Maybe they didn't survive at all. The cosmic dawn was a violent nursery riddled with supernova and gamma-ray bursts. A growing black hole could have been blasted apart by a nearby stellar explosion, its accretion disk disrupted before it could stabilize. Or perhaps mergers, the very process meant to bulk them up, kick them out of their host galaxies entirely, sending them drifting into intergalactic darkness like cosmic nomads. The implications ripple far beyond a simple missing link. If intermediate black holes truly are absent from the early universe, it challenges our entire understanding of how supermassive black holes got so big so fast. Without these stepping stones, theorists are forced to consider wilder possibilities like direct collapse black holes forming already massive, or exotic physics accelerating growth beyond known limits. Yet hope isn't lost. Recent gravitational wave detections hint at black holes in this elusive mass range, suggesting they might be out there, just harder to spot. And with new observatories like LISA set to scan the cosmos for their subtle ripples in spacetime, we might finally catch these cosmic middleweights in the act. Until then, their absence remains one of the cosmic dawn's quietest and most telling mysteries. In the darkest corners of the cosmic dawn, vast islands of glowing gas float like celestial ghosts, each one spanning hundreds of thousands of light years, radiating with a strange, ethereal light. These are Lyman-Alpha blobs, some of the most baffling structures in the early universe. Their glow comes from hydrogen atoms releasing ultraviolet photons, but what's lighting them up in the first place? That's where the mystery deepens. Picture a cloud so enormous it could swallow our Milky Way whole, shimmering with energy equivalent to billions of suns, yet with no obvious power source. Some blobs harbor fledgling galaxies at their cores, but their radiation alone can't explain the sheer scale of the glow. Others float in eerie isolation, untethered to any visible cosmic engine. It's like stumbling upon a city lit by invisible street lamps where the lights burn bright but no one can find the switch. One leading theory points to voracious black holes. As these monsters devour matter, their intense radiation could be ionizing the surrounding hydrogen, causing it to emit that distinctive Lyman-Alpha glow. But here's the catch. Many blobs show no signs of the high-energy emissions typically linked to black hole activity. Instead, their light is oddly smooth and uniform, more like the diffuse glow of a neon sign than the flickering flare of an accretion disk. Then there's the star formation angle. Massive starbursts within these blobs could be flooding them with ultraviolet light, energizing the gas. Yet when astronomers tally up the potential stars, the numbers rarely add up to the luminosity observed. Some blobs emit up to 10 times more energy than their visible galaxies should produce. It's as if we're only seeing the tip of an iceberg, with hidden stellar nurseries or even exotic objects like dark matter annihilations or primordial pulsars lurking beneath the surface. Perhaps the most tantalizing clue lies in the blob's intricate structures. Far from being shapeless clouds, many exhibit intricate filaments and bubbles, suggesting turbulent histories. Galactic winds from supernova might have carved these cavities, or perhaps the blobs are cosmic battlefield sites where calling gas streams ignite bursts of star formation before being shredded by violent feedback. Some models even propose these structures as the universe's original galaxy factories, where gravity and radiation worked in tandem to forge the first galactic clusters. What makes these blobs so critical is their timing. They appear precisely when the cosmos was transitioning from darkness to light, acting as cosmic beacons in an era of transformation. Their glow might hold secrets about how the first galaxies organized themselves, how dark matter distributed itself, even how the universe cleared its hydrogen fog during reionization. And with new instruments like the James Webb Space Telescope peering into their hearts, we're closer than ever to uncovering whether they're the nurseries of creation or the tombstones of forces we've yet to name. Galaxies are supposed to follow rules, especially when it comes to rotation. The faster they spin, the more mass they should contain, with invisible dark matter providing the extra gravitational glue to keep everything from flying apart. But the cosmic dawn has a habit of breaking expectations, and here's the latest curveball. Some of the earliest galaxies are spinning at breakneck speeds that defy all logic. These cosmic speed demons shouldn't exist, at least not according to our models of how galaxies form and evolve. Yet there they are, twirling like ballerinas in the void, their stars and gas whirling so fast that they ought to tear themselves apart. Either we're missing something fundamental about dark matter, or the early universe played by a completely different set of physics. Take one recently observed galaxy from when the universe was just 500 million years old. Based on its brightness and size, it should have been a lightweight, rotating at a modest pace. Instead, measurements revealed a spin rate comparable to the Milky Way, a galaxy that's had over 13 billion years to grow and accumulate mass. It's the equivalent of finding a toddler bench pressing twice their body weight. The numbers just don't add up. Dark matter should have been too thinly spread in the early cosmos to anchor such rapid rotation, leaving theorists scrambling for explanations. One possibility is that dark matter behaved differently back then. Today, it's thought to clump sluggishly, forming diffuse halos around galaxies. But simulations suggest that if dark matter particles interacted with each other through some unknown force, they could have pooled into denser, more concentrated configurations in the cosmic dawn, bolstering galaxies' rotation speeds from the start. Imagine stirring honey versus water. The thicker fluid would create tighter whirls. Similarly, a more sticky form of dark matter might have allowed early galaxies to spin faster without flying apart. Then there's the wild card. Maybe dark matter isn't the culprit at all. Alternative theories of gravity, like modified Newtonian dynamics propose that our understanding of gravitational forces breaks down at galactic scales. In these models, no dark matter is needed. The laws of physics themselves adjust to explain the rotation. But even struggles with the extreme speeds seen in these primordial galaxies, leaving researchers to wonder if an even more radical rewrite is needed. Could spacetime itself have been different in the early universe, warped by energies we've yet to account for? The plot thickens when we look at how these fast-spinning galaxies are built. Many show bizarre, disk-like structures that are far more organized than predicted for their age. Normally, young galaxies are messy, turbulent places, still reeling from chaotic collisions and bursts of star formation. But these cosmic disks are oddly serene, their rotations smooth and stable, as if they'd had billions of extra years to settle down. It's another layer to the paradox. Not only are they spinning too fast, they're also too mature for their age. What makes this mystery so urgent is its ripple effect. Galactic rotation isn't just about motion, it's a window into how structure emerges in the cosmos. If we've misjudged the rules for these early galaxies, it could mean recalculating everything from dark matter distributions to the timeline of cosmic evolution. Future telescopes like the Square Kilometre Array aim to measure hydrogen gas in these ancient whirlpools with unprecedented precision, potentially revealing whether our theories need a tweak or a total overhaul. Until then, these hyperactive galaxies remain one of the cosmic dawn's most tantalizing glitches, a reminder that the universe's first chapters still hold secrets we've only begun to decode. What if the cosmic dawn wasn't just shaped by the usual suspect stars, galaxies, dark matter, but by shadows left over from the birth of the universe itself? Primordial black holes, hypothetical remnants of the Big Bang's violent infancy, could be the unseen puppeteers behind some of the era's most baffling anomalies. These aren't the black holes we know today, forged from dying stars or galactic collisions. These would be relics from the universe's first chaotic moments, when density fluctuations in the searing hot plasma collapsed directly into black holes, some as small as asteroids, others rivaling entire solar systems in mass. And if they exist, they might be hiding in plain sight, masquerading as dark matter or seeding the supermassive monsters we find in the early cosmos. The theory is as elegant as it is contentious. Dark matter's gravitational effects are undeniable, but we've never directly detected its particles. Primordial black holes offer a radical alternative. What if dark matter isn't a mysterious particle at all, but countless ancient black holes sprinkled across the cosmos? It's a tantalizing solution to multiple puzzles at once. These black holes would have formed before the cosmic dawn, invisible to telescopes yet bending spacetime with their gravity. They could explain why some early galaxies rotate too fast, their extra mass hidden in these primordial traps. They might even be the missing seeds for supermassive black holes, growing silently in the darkness long before the first stars flickered to life. But here's the catch: finding them is like searching for ghosts. Primordial black holes wouldn't emit Hawking radiation unless they're very small, and those tiny ones would have evaporated by now. Larger ones, between the mass of a mountain and a star, could still lurk undetected. Occasionally, one might pass in front of a distant star, its gravity bending the light in a telltale flash called microlensing. Surveys have looked, but so far the numbers don't add up to account for all dark matter. That hasn't killed the idea, though. Maybe primordial black holes are rarer than hoped, contributing only a fraction of dark matter's heft. Or perhaps they congregate in halos around galaxies, avoiding detection in the voids where we typically search. The cosmic dawn offers another way to test the theory. If these black holes were abundant early on, their gravity would have subtly influenced the formation of the first stars and galaxies. Some simulations suggest they might have accelerated structure formation, creating unusually dense pockets of matter that collapsed into stars faster than expected. Others propose they could have kick-started reionization, their accretion disks spewing radiation that stripped electrons from hydrogen atoms. Even stranger, collisions between primordial black holes might have produced gravitational waves detectable today, ripples in space-time that could carry fingerprints from the universe's first nanoseconds. Yet for all its promise, the idea faces fierce skepticism. The conditions needed to form primordial black holes in the Big Bang are absurdly fine-tuned, requiring density fluctuations far more extreme than those seen in the cosmic microwave background. Plus, their existence would have left scarce distortions in the cosmic microwave background or overabundances of certain elements from their violent interactions. None of these signatures have turned up definitively. The debate rages on, but one thing is certain. If primordial black holes are real, they're rewriting cosmic history from the shadows. Whether as dark matter candidates, galactic architects, or something even stranger, they remind us that the universe's first moments might hold keys we've only begun to imagine. And with new gravitational wave detectors and next-gen telescopes joining the hunt, we might finally uncover whether these phantom remnants are fact or just a beautiful, elusive myth. Gas clouds in the cosmic dawn should have been hot, searing, turbulent cauldrons of hydrogen boiling under the radiation of the first stars. That's what our models predicted. But the universe loves a good surprise. When astronomers measured the temperature of these ancient gas clouds using subtle radio signals, they got a shock. The clouds were freezing. Not just cooler than expected, but colder than the cosmic microwave background itself, as if some cosmic refrigerator had switched on in the early universe. This isn't just a minor discrepancy, it's a full-blown thermodynamic paradox, and it might rewrite what we know about the first stars' lives and deaths. The key lies in a phenomenon called the 21-centimeter line, a faint radio whisper emitted by neutral hydrogen atoms. By studying how this signal gets absorbed or amplified, we can deduce the gas's temperature. In a region bombarded by starlight, hydrogen should heat up, its atoms excited by ultraviolet photons. Yet across vast swaths of the early cosmos, the opposite happened. The gas chilled, dropping tens of degrees below the ambient temperature of deep space. Something was siphoning energy away, and whatever it was, it worked with frightening efficiency. One clue comes from the first stars themselves. These primordial giants made of pure hydrogen and helium might have burned differently from modern stars, hotter in some ways, but emitting a distinct spectrum of light. If their radiation peaked at just the right energy, it could have triggered a cooling effect in the surrounding hydrogen, like cosmic air conditioning. Picture a laser cooling trapped atoms in a lab, and you've got the basic idea. But scaling this up to interstellar clouds requires conditions so precise it borders on alchemy. Then there's dark matter's potential role. Some theories suggest certain dark matter particles could interact with hydrogen, exchanging heat in ways we don't yet understand. If these particles were slightly warm, moving just fast enough to carry away energy, they might explain the anomalous chill. Others propose that cosmic rays from the first supernova ripped through the gas, stripping electrons and leaving behind cooler pockets. It's counterintuitive, but ionized gas can actually lose heat more efficiently than neutral gas under certain conditions. The coldest clouds of all pose the biggest riddle. In regions far from any known galaxies, temperatures plunge inexplicably low. These cosmic deep freezes hint at forces we've yet to identify, perhaps exotic molecules forming in the gas or primordial magnetic fields dissipating energy. There's even speculation that quantum effects, amplified by the vast scales of the early universe, played a role we're only beginning to grasp. What makes this mystery so urgent is its domino effect. Gas temperature isn't just trivia, it controls whether clouds collapse into stars or linger in stagnation. These chilly conditions might have delayed galaxy formation in some regions while accelerating it in others, creating the patchwork universe we see today. And if the cooling mechanism was something beyond known physics, it could point toward entirely new cosmic phenomena. With new radio telescopes like the Square Kilometre Array tuning into these ancient whispers, we're closer than ever to cracking the case. Every anomalous chill in the data is a breadcrumb leading us toward a deeper truth. The cosmic dawn wasn't just about light conquering darkness. It was a battleground of energies where heat and cold waged a silent war, and we're only now discovering who won. Simulations paint a crowded picture of the early universe, a cosmic metropolis teeming with thousands of dwarf galaxies swarming around larger ones like fireflies around a lantern. But when astronomers look up, the night sky tells a different story. Where theory predicts multitudes, observations reveal only scattered handfuls. This glaring mismatch, known as the missing satellites problem, isn't just a minor accounting error. It's a fundamental crack in our understanding of how structure unfolded after the cosmic dawn. Either these galaxies are hiding in plain sight, or something in our most trusted models is profoundly wrong. For decades, dark matter simulations suggested that the Milky Way alone should have hundreds of satellite dwarf galaxies, relics from the universe's first billion years. Yet we've confirmed barely 60, and most are frustratingly dim. The discrepancy grows worse when we peer back to the cosmic dawn, where sensitive telescopes like the James Webb should be spotting these fledgling systems by the dozens. Their absence forces an uncomfortable question. Did dwarf galaxies fail to form as predicted, or did they form and then vanish? One camp argues we're simply not seeing them, that these cosmic minnows are so faint, their starlight drowned in the glare of foreground objects or stretched into invisibility by cosmic expansion. Finding them would require detecting individual stars against the blackness of intergalactic space, like spotting fireflies from a mountaintop at midnight. Recent ultra-deep surveys have uncovered a few previously hidden dwarfs, but not nearly enough to close the gap. Some theorists suggest an even sneakier possibility, that many of these galaxies are almost entirely dark matter, with so few stars they're virtually transparent. Then there's the nuclear option that our simulations are missing a critical piece of physics. Dark matter's behavior might be more complex than we've assumed, perhaps interacting with itself or with radiation in ways that suppressed small galaxy formation. Alternatively, the intense ultraviolet light from the first stars could have heated intergalactic gas, preventing it from cooling and collapsing into dwarfs. The most radical proposals even challenge galaxy formation itself, suggesting early dwarf galaxies were systematically shredded by tidal forces or blasted apart by supernova before they could mature. The stakes couldn't be higher. Dwarf galaxies aren't just cosmic accessories, they're the building blocks of larger galaxies, the fossil record of the universe's growth. If they're truly missing, it implies the cosmic dawn played out under different rules than we thought, with dark matter distributed differently or gravity itself behaving oddly at small scales. Every undiscovered dwarf is a clue waiting to be found, a whisper from an era when the universe was still writing its own rulebook. New infrared telescopes and gravitational lensing surveys are finally bringing these shadows into focus. With each discovery, we edge closer to solving whether the fault lies in our eyes or in our theories. Until then, the missing satellites remain one of the cosmic dawn's most persistent ghosts, reminding us that sometimes what we don't see teaches us more than what we do. Imagine a signal so powerful it outshines entire galaxies, but only for a millisecond. Fast radio bursts, or FRB, are some of the most enigmatic flashes in the universe, packing more energy than the sun emits in decades into a blink and you'll miss it pulse. Most come from billions of light years away, but a handful appear to echo from the cosmic dawn itself. That raises an electrifying question. Could these mysterious bursts be the death cries of the first stars, the birth pangs of primordial black holes, or even evidence of physics we've yet to discover? The leading suspects are magnetars, ultra-dense neutron stars with magnetic fields so intense they could strip atoms apart from thousands of miles away. When these cosmic powerhouses undergo starquakes or magnetic eruptions, they might unleash FRBs like celestial lightning strikes. But here's the twist: magnetars are the corpses of massive stars, and in the cosmic dawn, those stars were just beginning to die. For FRBs to originate from this era, magnetars would have had to form impossibly fast, their parent stars living and dying in cosmic microseconds, unless, of course, something else was at work. One tantalizing possibility involves black holes of a different breed. If the early universe birthed asteroid mass, primordial black holes, leftover knots of density from the Big Bang, their collisions or evaporation could generate bursts matching FRB profiles. Picture two microscopic black holes spiraling together, their final moments unleashing a ripple of energy detectable across billions of years. Even stranger, certain unified field theories predict cosmic strings, defects in spacetime itself, vibrating like snapped guitar strings to produce these flashes. Then there's the wild card: could FRBs be artificial? The idea isn't as far-fetched as it sounds. A sufficiently advanced civilization might harness black holes or neutron stars as galactic-scale beacons, their pulses engineered to punch through intergalactic static. While there's zero evidence for this, the sheer regularity of some repeating FRBs has sparked debates about whether natural processes could really be so precise. What makes cosmic dawn FRBs uniquely thrilling is their potential as probes. As these signals traverse the early universe, they interact with the sparse hydrogen fog, encoding its density and distribution in their radio fingerprints. A single burst could map the invisible scaffolding of dark matter or reveal pockets of ionized gas from the first stars. New telescopes like CHIME and the upcoming Square Kilometre Array are turning FRB detection into a cosmic census, each flash a time capsule from an era we've barely begun to explore. Whether they're stellar catastrophes, space-time quakes, or something beyond our imagination, one thing's certain: these millisecond mysteries are rewriting the story of the cosmic dawn. And with every new burst, we're one step closer to uncovering whether they're cosmic accidents or deliberate messages from the universe's first chapter. Magnetism shouldn't have existed in the cosmic dawn, at least not the way we understand it today. In a universe barely a billion years old, before the first stars forged heavy elements and supernova scattered them across space, there should have been almost nothing to generate or sustain magnetic fields. And yet, when astronomers study light from that era, they find subtle signatures of magnetism imprinted on ancient gas clouds and fledgling galaxies. These fields are weak, a million times fainter than Earth's, but their mere presence is a paradox. How could cosmic magnetism arise so soon, and what seeded it? The answers might rewrite not just galactic history, but the very laws of physics. One camp argues these fields were primordial, woven into the fabric of spacetime during the Big Bang itself. Picture the universe's birth as a cosmic loom, with quantum fluctuations stitching magnetic threads into existence as space expanded. These minuscule fields, weaker than a fridge magnet stretched across light years, could have been amplified over eons by the motion of ionized gas. It's a compelling idea, but there's a catch. no known physics predicts how such fields could survive the universe's hot, chaotic infancy. The inflationary epoch should have erased them like a cosmic reset button. Unless, of course, inflation left behind wrinkles we've yet to discover, hidden defects in spacetime that preserved magnetic imprints like fossils in amber. Then there's the stellar afterparty theory. The first stars, though short-lived, were factories of chaos. Their violent deaths in supernova could have churned surrounding gas into turbulent dynamos, generating localized magnetic fields like whirlpools in a cosmic river. Over time, these pockets might have merged and grown, seeding entire galaxies with magnetism. But observations throw a wrench in this tidy story. Some of the earliest magnetic fields appear too widespread, too uniform to stem from scattered stellar explosions. They're more like a faint background hum than isolated sparks, an eerie symmetry that hints at deeper origins. The plot thickens when we consider black holes. Active galactic nuclei, powered by supermassive black holes, spewed jets of plasma that could magnetize vast regions of intergalactic space. Yet these monsters needed time to grow, leaving us with another chicken and egg problem. Did magnetism enable black holes to form, or did black holes create the magnetism? The wildest theories suggest both that primordial fields guided gas into early black holes, which then turbocharged those same fields in a feedback loop of cosmic proportions. What makes this mystery so urgent is its ripple effect. Magnetic fields shape how galaxies form stars, how cosmic rays travel, even how planets like Earth develop protective shields. If the seeds were planted in the cosmic dawn, their legacy is written into every spiral arm and nebula we see today. New telescopes like the Square Kilometre Array are mapping these ancient fields with unprecedented precision, tracing their fingerprints back to the universe's first chapters. Whether primordial or forged in stellar fires, one thing's clear: magnetism didn't wait for permission to shape the cosmos. It emerged from the shadows, silent and unstoppable, and we're only beginning to understand its origins. Among the first flickers of light in the cosmic dawn, there might have been stars unlike any we've ever seen, not burning with nuclear fire, but glowing with something far stranger: the annihilation of dark matter. These hypothetical dark stars could rewrite the story of how the universe woke up, offering answers to some of the era's most perplexing gaps. Imagine a celestial body so massive it dwarfed modern stars, fueled not by fusion but by particles colliding in its core, unleashing energy in a slow, eerie burn. If they existed, these dark stars would have been the universe's first lanterns, monstrous, luminous, and utterly alien. The concept hinges on a radical idea: that dark matter isn't just an invisible scaffold for galaxies, but an active participant in stellar physics. In the dense environments of the early universe, dark matter particles, whatever they are, could have clustered at the hearts of collapsing gas clouds. If those particles occasionally collide and annihilate, converting their mass into energy, they'd generate heat to oppose gravitational collapse. The result: a star that never ignites fusion, yet shines for millions or even billions of years, powered entirely by the slow decay of the universe's most mysterious substance. What makes this theory so compelling are the cosmic quirks it might explain. Some of the early universe's inexplicably bright galaxies could harbor dark stars at their cores, their unusual luminosity coming from dark matter's relentless annihilation. Others might have seeded the first supermassive black holes, their dark cores growing unstable before collapsing into voids of unimaginable density. Even the timing of reionization, that great clearing of the cosmic fog, could fit better if dark stars were pumping out steady, diffuse radiation long before conventional stars took over. Detecting these phantoms, though, is a challenge worthy of their mystery. A true dark star would emit a peculiar spectrum cooler than a fusion-powered star of similar size, yet rich in infrared and ultraviolet light from annihilating dark matter. The James Webb Space Telescope might have already glimpsed candidates, bizarre objects too red and too large to fit known stellar models, lurking in the deepest reaches of its infrared gaze. Gravitational lensing could offer another clue, as the immense mass of a dark star would bend light in ways distinct from ordinary stars or black holes. Yet the most tantalizing evidence might come from what dark stars left behind. If they collapsed into black holes, their remnants could explain the sudden appearance of supermassive giants in the early cosmos. Alternatively, their slow-burning nature might have allowed them to survive longer than fusion stars, leaving faint, lingering embers that modern telescopes could still spot. Either way, their existence or absence holds profound implications. Dark stars aren't just curiosities, they're a test of whether dark matter interacts with itself in ways we've yet to imagine. The hunt for these cosmic anomalies is more than a niche puzzle, it's a doorway into dark matter's hidden physics. Every unusual glimmer from the cosmic dawn could be a signature waiting to be decoded. And if we find them, it won't just change how we see the universe's first light. It'll reveal that the cosmos has been keeping secrets far stranger than we ever dreamed. The universe wasn't supposed to have chemistry this early. In the cosmic dawn, when the first galaxies were still taking shape, the periodic table should have been nearly empty, just hydrogen, helium, and trace amounts of lithium forged in the Big Bang's afterglow. Heavy elements like carbon, oxygen, and iron require stellar furnaces to cook them, and those furnaces needed time to ignite, burn, and explode. Yet when astronomers point telescopes like the James Webb at galaxies barely 700 million years old, they find fingerprints of these metals stamped across their spectra. It's as if we've stumbled into a cosmic kitchen where the first bakers somehow whipped up a 5-course meal before the oven even finished preheating. The culprit, population 3 stars, those mythical first-generation giants made of pure primordial gas. Conventional wisdom says they lived fast and died young, exploding as supernova that seeded the cosmos with its first heavy elements. But the sheer abundance of these metals in certain early galaxies suggests something more extreme. These stars might not just have died, they could have died spectacularly, in hypernova or pair instability, supernova so violent they ripped apart entire stellar cores, blasting their elemental guts across interstellar space at unprecedented scales. Imagine a firework designed by a mad scientist, one that doesn't just sparkle but atomizes itself into a cloud of glitter that lingers for eons. That's the kind of stellar death we're talking about. There's just one problem. Even these cosmic mavericks might not be enough. Some early galaxies show metal enrichment levels rivaling the Milky Way's, a feat requiring not just a few supernova, but legions of them, working in concert like an assembly line of elemental production. Did population 3 stars form in dense, hyper-efficient clusters, their combined explosions creating localized pockets of extreme chemistry, or was there another, even more exotic contributor? Enter the dark horse of the cosmic dawn, supermassive stars. Theoretical models suggest that under perfect conditions, pristine gas clouds free of turbulence or competing star formation, a single star could balloon to masses exceeding 100,000 suns. These leviathans wouldn't just forge heavy elements, they'd mass-produce them, their internal pressures reaching extremes where nuclear reactions cascade like dominoes. When these monsters finally collapsed, they wouldn't leave behind black holes, they'd vanish in annihilation events so bright they'd outshine entire galaxy clusters, scattering metals like cosmic shrapnel. Yet the plot thickens when we consider alternative pathways. Could early black holes have played metallurgist, their accretion disks churning out heavy elements like cosmic assembly lines? Some quasars show bizarre emission lines hinting at nickel and zinc, elements typically forged in environments far hotter than standard stellar cores. Or perhaps the answer lies in neutron-star mergers, those rare collisions that sprinkle gold and platinum across the cosmos like celestial confetti. The trouble is, these events are supposed to be rare, especially in the universe's first billion years. Unless the cosmic dawn was somehow a golden age for neutron star rendezvous, their contributions might not add up. The implications ripple far beyond astrophysics. Heavy elements are the building blocks of planets' life, even the screen you're watching this on. If they appeared earlier than thought, it reshapes our entire timeline for when habitable worlds could have formed. Somewhere out there, a rocky planet might have circled a metal-rich star when Earth was still a swirl of gas in the void. And with telescopes peeling back the layers of these ancient galaxies, we're closer than ever to solving whether the universe's first chemistry set was stocked by familiar processes or something far more extraordinary. Stretching across the cosmos like a phantom fog, the cosmic infrared background hums with light we can't quite place, a diffuse glow that shouldn't exist. When astronomers tally up all the known galaxies from the cosmic dawn, their combined starlight falls drastically short of explaining this pervasive infrared haze. It's as if the universe left every light on, but half the bulbs are missing. So what's casting this ghostly radiance? The answer might rewrite what we know about the universe's first chapters, revealing hidden stellar nurseries, rogue black holes, or even phenomena we've yet to name. One leading theory points to a shadow population of dwarf galaxies, tiny, faint systems too dim for our telescopes to spot individually, but collectively bright enough to paint the cosmos in infrared. Picture a vast field of fireflies, each one invisible to the naked eye, but together creating a shimmering veil. These galaxies could be churning out stars at rates that defy expectations, their light stretched and reddened by cosmic expansion until it blends into the infrared background. The James Webb Space Telescope has already glimpsed hints of these hidden builders, detecting galaxies so distant and diffuse they barely register as smudges. Yet even these discoveries might be the tip of the iceberg, with simulations suggesting legions of ultra-faint galaxies still lurk beyond our view. But there's a twist. Some regions of the infrared glow are too intense, too clumpy to stem from galaxies alone. This has led theorists down stranger paths. Could primordial black holes, those hypothetical remnants of the Big Bang, be heating surrounding dust with their radiation, creating infrared hotspots? Or might dark matter itself be decaying or annihilating in pockets of the early universe, releasing energy as subtle heat? The wildest proposals even entertain cosmic strings, defects in space-time left over from the universe's birth, vibrating like plucked guitar strings to emit infrared waves. The plot thickens when we examine the glow's uneven distribution. Instead of a smooth curtain of light, it's patchy with bright knots and dark voids. Some patches align eerily with known galaxy clusters, suggesting their light is being magnified by gravitational lenses, invisible masses bending space-time to amplify distant emissions. Others float in isolation, untethered to any visible structure. These anomalies hint at a cosmos far messier and more dynamic than we imagined, where star formation might have occurred in explosive bursts or where entire galaxies flared up and vanished before leaving traces we can recognize. What makes this mystery so tantalizing is its reach. The cosmic infrared background isn't just stray light. It's a fossil record of the universe's toddler years, encoding secrets about how structure emerged from the primordial dark. If we can decode its patterns, we might uncover missing chapters in galactic evolution, or even catch whispers of physics beyond our current theories. With every new infrared survey, we're peeling back layers of this cosmic onion, revealing just how much of the universe's early story remains hidden in plain sight. Galaxies don't just drift alone in the void, they gather, drawn together by gravity into sprawling metropolises we call clusters. But when we peer back to the cosmic dawn, these clusters didn't form slowly, brick by brick, over billions of years. No, they erupted into existence almost overnight on cosmic timescales, assembling with a speed that defies everything we thought we knew about cosmic structure. These protoclusters, the infant versions of today's galaxy clusters, should have taken eons to coalesce. Instead, they're caught on camera fully formed when the universe was barely a tenth of its current age. It's like finding a bustling city where yesterday there was only wilderness. So what cosmic shortcut allowed these giants to rise so fast? The plot thickens when we examine the forces at play. Gravity alone can't explain such rapid growth. It's too slow, too methodical for the breakneck pace we observe. Enter dark energy, that mysterious force accelerating the expansion of the universe today. Could it have behaved differently in the cosmic dawn, somehow switching roles from cosmic brake pedal to accelerator? Some models suggest that in the early universe's denser environment, dark energy might have acted counterintuitively, temporarily amplifying gravitational collapse in localized regions. Picture a tide that instead of receding, surges inward, piling water into sudden, towering waves. That's the kind of anomaly we're dealing with, yet dark energy isn't the only suspect. Modified gravity theories like MUND or their more exotic cousins propose that gravity itself might have played by different rules when the cosmos was young. In these scenarios, the pull between galaxies could have been stronger in the denser early universe, creating a sort of gravitational stickiness that glued protoclusters together at impossible speeds. Imagine trying to build a sandcastle with dry sand. It's nearly impossible, but add water and the grains suddenly cling, forming structures almost instantly. If gravity had an extra cling factor in the cosmic dawn, it could solve the protocluster paradox, but here's where observations throw a wrench in the works. Some of these early protoclusters aren't just dense, they're bizarrely organized, with galaxies aligned in filaments and sheets that resemble cosmic spiderwebs. Such intricate structures usually require time to develop, the result of countless gentle interactions over billions of years. Yet these webs appear fully spun in the blink of a cosmic eye. It's as if the universe had a prefabricated template, a hidden blueprint that allowed clusters to snap into place like pieces of a preordained puzzle. The implications are staggering. If protoclusters grew via unknown physics, it would mean the universe's large-scale structure wasn't built solely by gravity's patient hand. Something else, something hidden in the equations or lurking in the shadows of our models, gave it a head start. Future telescopes like the Roman Space Telescope aim to map these protoclusters in 3D, tracing their growth with forensic precision. Each new snapshot from the cosmic dawn brings us closer to uncovering whether dark energy, gravity, or something entirely unexpected engineered this great cosmic speedrun. One thing's certain, the universe didn't just grow up. It exploded into maturity, leaving behind clues that challenge our most fundamental assumptions. And somewhere in those ancient clusters lies the answer to how the cosmos built its greatest structures, not over time, but in a flash. Planets weren't supposed to exist this early. In the cosmic dawn, the universe was still a chaotic construction site, gas clouds swirling, stars igniting, galaxies struggling to take shape. The idea of stable, rocky worlds coalescing in such turbulence seemed almost absurd. And yet, the deeper we look, the more we realize the first planets might not have waited for permission to form. They could have been born in the fire and fury of the universe's first breaths, orbiting stars so ancient they burned out before our solar system even existed. These wouldn't be planets as we know them, no familiar continents, no oceans, no oxygen-rich skies. They'd be relics of a time when the periodic table itself was still being forged, worlds sculpted from the barest scraps of heavy elements. Take the case of population 3 stars again, those primordial giants made only of hydrogen and helium. When they died in supernova, they scattered the first heavy elements into the cosmos, seeding the clouds that would birth the next generation of stars. But what if, in those violent afterglows, specks of carbon, silicon, and iron managed to clump together before being blown apart? Simulations suggest that under just the right conditions, tiny grains could have stuck together in the dense winds of stellar explosions, forming planetesimals in miniature. These wouldn't be Earth-like worlds, they'd be bizarre, metallic spheres, perhaps no larger than asteroids, with surfaces of pure graphite or crystallized titanium. Imagine a world where mountains are made of solid diamond, where the rain is liquid iron, and the sky burns with the ultraviolet glare of a young, furious star. Detecting these ancient worlds is another challenge entirely. Light from the cosmic dawn has been stretched into the infrared by the expansion of the universe, dimmed to near invisibility. A planet orbiting one of these early stars would be a whisper lost in the noise of cosmic background radiation. Even if we could spot one, its composition would defy all our expectations. Without oxygen or water, these planets wouldn't reflect light the way modern worlds do. Their atmospheres, if they had any, might be soups of hydrogen, helium, and trace metals, stripped away by the relentless radiation of their host stars. Some could even be rogue planets flung from their orbits by gravitational chaos, drifting through the void like frozen time capsules from the universe's first chapters. The hunt isn't hopeless, though. Gravitational microlensing, the bending of light around massive objects, offers one tantalizing path. If a primordial planet passed in front of a distant star, its gravity could warp the star's light in a telltale flicker. The James Webb Space Telescope, with its infrared vision, might catch the thermal glow of a lone world, cooling in the darkness long after its star has died. And then there's the wild card, pulsar planets. We've already found worlds orbiting the corpses of dead stars in our own galaxy, proving that planets can form or survive in the most extreme conditions. If pulsar planets exist today, why not in the cosmic dawn? But the most profound question isn't just whether these planets existed, it's what happened to them. Some might have spiraled into their stars, consumed by gravitational tides. Others could have collided, their debris recycled into the next generations of stars and worlds. A handful might still linger, frozen relics adrift between galaxies, their surfaces untouched by time. And if by some impossible chance life did emerge on one, it would have faced a universe far harsher than our own, bathed in radiation, devoid of the rich chemistry we take for granted. Yet the mere possibility forces us to reconsider the timeline of life itself. If planets existed in the cosmic dawn, the story of life in the universe might be older, stranger, and more resilient than we ever dreamed. The search for these lost worlds is more than a niche obsession. It's a window into the universe's capacity for creation under the most hostile conditions. Every exoplanet discovered today owes its existence to those first, tentative steps in the cosmic dawn. And if we ever find one, it won't just be a scientific breakthrough. It'll be a message from the dawn of time itself, a reminder that planets and perhaps life found a way even when the universe was still learning the rules. One of the strangest signals from the cosmic dawn isn't light at all, it's silence. When astronomers tuned their radio telescopes to listen for the faint whispers of neutral hydrogen, they expected to hear a steady hum. Instead, they caught a cosmic murmur that sent shockwaves through astrophysics. The 21-centimeter line, a fingerprint left by hydrogen atoms shifting their quantum states, revealed something impossible. Patches of the early universe were colder than the cosmic microwave background itself. It's as if the universe turned on a celestial air conditioner before the first stars even finished flickering to life. Let's unpack this cosmic chill. Normally, hydrogen gas absorbs background radiation when it's cooler than its surroundings, imprinting a telltale dip in the 21-centimeter signal. But the depths of these dips don't just hint at a slight temperature difference, they suggest pockets of gas plunging dozens of degrees below the ambient warmth left over from the Big Bang. Picture stepping into a forest and finding frost clinging to leaves in the middle of summer. The laws of thermodynamics say this shouldn't happen naturally, yet there it is, etched into radio waves from 13 billion years ago. So what could trigger such extreme cooling? One leading theory points to the first stars, but not in the way you'd expect. These primordial giants emitted ultraviolet light at precise wavelengths capable of exciting hydrogen atoms, making them more likely to interact with the cosmic microwave background and shed heat. It's a process called the Woutheisen field effect, a quantum quirk that essentially lets starlight act as a refrigerant for the cosmos. But there's a catch: the cooling seems too widespread, too efficient for stars alone to be responsible. Even if every known early galaxy worked overtime, they couldn't explain the scale of the chill. Then there's dark matter's shadowy role. If certain hypothetical particles like weakly interacting massive particles or WIMP collided with hydrogen, they could transfer energy away from the gas, cooling it like invisible ice cubes dropped into a cosmic drink. Another proposal involves primordial magnetic fields woven into space during the universe's birth, stirring the hydrogen into vortices that radiated away heat. The wildest ideas even flirt with quantum vacuum effects, where fluctuations in spacetime itself siphoned energy from the gas. But the coldest regions defy all these explanations. In these voids, far from any known galaxies, temperatures drop so low that conventional physics struggles to account for it. Some theorists suggest we're seeing echoes of a pre-stellar era when exotic particles or fields dominated the cosmos. Others propose these patches are the scars of cosmic strings, defects in spacetime left over from the Big Bang that shredded the hydrogen's thermal equilibrium. What makes this mystery so urgent is its ripple effect. The temperature of early hydrogen didn't just influence star formation, it dictated where and when galaxies could ignite. Too cold and gas collapses too readily, birthing starbursts that burn out fast. Too warm and galaxies struggle to form at all. This delicate thermal dance might explain why the universe looks the way it does and why simulations so often fail to match reality. New radio telescopes like the Square Kilometre Array are now mapping these ancient temperature fluctuations in unprecedented detail. Every anomalous cold spot is a clue, a whisper from an era when the universe's thermostat malfunctioned in ways we're only beginning to grasp. Whether the culprit turns out to be dark matter, exotic stars, or something entirely unknown, one thing's clear: the cosmic dawn wasn't just about light piercing the darkness. It was a battle between heat and cold that shaped everything we see today. Galaxies today are master regulators, balancing star birth and death with an elegance that seems almost choreographed. Supernova explode, black holes belch radiation, and stellar winds push away gas, all working in concert to prevent runaway star formation. But rewind to the cosmic dawn, and this delicate feedback system vanishes. The earliest galaxies shouldn't have been able to control themselves. Without heavy elements, stellar winds were weaker. Without well-fed black holes, radiation pressure was sporadic. Yet somehow, these chaotic young galaxies didn't burn through their fuel in a single, catastrophic starburst. They somehow found balance, and we're only beginning to understand how. Take supernova, the universe's original feedback mechanism. When the first stars, those monstrous population, three giants, reached the ends of their lives, their deaths weren't just explosions. They were thermonuclear detonations so violent they could vaporize entire gas clouds, shutting down star formation across vast swaths of space. But here's the catch: these supernovae were also rare. With fewer stars in the early universe, their explosions should have been isolated events like scattered firecrackers in a dark field. Yet the cosmic record shows something different, an eerie uniformity in early galaxy growth, as if some unseen hand smoothed out the chaos. That hand might have been radiation pressure, but not the kind we know today. Modern stars are wrapped in heavy elements, their light absorbed and re-radiated by dust grains. In the primordial universe, dust didn't exist. Instead, pure ultraviolet light from the first stars could have pushed directly against hydrogen atoms, driving gas outward in vast, gentle waves. Picture sunlight pressing against a solar sail, but on a cosmic scale, with enough force to sculpt galaxies. This line-driving effect might have been subtle, but over millions of years, it could have prevented gas from collapsing too quickly, regulating star birth without the need for supernova or black holes. Then there's the wild card, cosmic turbulence. The early universe was a maelstrom of merging gas clouds and colliding dark matter halos. This chaos didn't just stir the pot, it could have acted as a natural regulator. Turbulence creates pressure, preventing gas from settling into the calm, dense pockets needed for rapid star formation. In a sense, the cosmic dawn's violence might have been its own brake, keeping galaxies from burning too bright too fast. It's a delicate dance. Too much turbulence and stars never form, too little and galaxies overheat. The fact that early galaxies walked this tightrope at all suggests a universe fine-tuned for balance even in its wildest youth. But the most tantalizing clue lies in black holes, not the supermassive ones we know today, but their smaller, more erratic ancestors. Recent simulations suggest that mini-quasars, powered by intermediate mass black holes, could have belched just enough radiation to disrupt star formation without quenching it entirely. These smaller engines wouldn't shine as brightly as their modern counterparts, but their frequent outbursts might have been enough to keep star formation in check. Think of it like a campfire stoker, not dousing the flames, but adjusting the logs to keep the fire burning steady. The implications ripple far beyond astrophysics. Feedback isn't just about galaxies, it's about how structure emerges in the universe. Without these early balancing acts, galaxies might have exhausted their gas before life ever had a chance to emerge. The cosmic dawn's missing feedback link isn't just a puzzle, it's a clue to why the universe looks the way it does and why we're here to ponder it at all. Galaxies in the cosmic dawn weren't supposed to be loners. The early universe was a crowded construction zone, dark matter clumping into filaments, gas swirling into dense knots, and proto-galaxies colliding in a frenzied dance of creation. So when telescopes like the James Webb began spotting galaxies floating in eerie isolation, untouched by neighbors for millions of light years, astronomers did a double take. These cosmic hermits shouldn't exist, not unless our models of structure formation are missing a crucial piece of the puzzle. Take one recently discovered galaxy from just 600 million years after the Big Bang. Its light suggests it's massive, teeming with stars, yet it sits in a region of space so empty it's like a single skyscraper in the middle of a desert. By all accounts, such a galaxy should have been born in a dense cluster, surrounded by siblings and satellites. Instead, it's utterly alone, as if it formed in defiance of gravity itself. The strangest part, it's not the only one. Dozens of these solitary giants pepper the cosmic dawn, their existence posing a haunting question. Did they form in place against all odds, or were they brutally divorced from their surroundings by forces we don't yet understand? One theory suggests these galaxies might be cosmic castaways ejected from their birth clusters by gravitational slingshots during violent mergers. Picture a pinball machine on a galactic scale, where fledgling galaxies could be flung into the void by the sheer momentum of collisions. But simulations show this is astronomically rare. The energy required to eject an entire galaxy would likely tear it apart in the process, unless, of course, the early universe hosted hyper-efficient gravitational kicks we've never observed, some quirk of space-time or dark matter that amplified these events. Then there's the dark matter dilemma. If dark matter in the cosmic dawn was clumpier than predicted, forming dense, isolated halos rather than smooth webs, it could have allowed galaxies to condense in pockets of space untouched by larger structures. Think of it like dew forming on a spiderweb. Most droplets cluster where the strands intersect, but a few stubborn beads cling to lone threads. Some modified gravity theories even propose that dark matter's pull was stronger in certain regions, creating gravitational wells deep enough to trap gas and form galaxies far from the cosmic crowd. But the radical possibility is that these galaxies never had neighbors to begin with. Alternative models of inflation, the universe's exponential expansion in its first moments, suggest that quantum fluctuations could have created bubbles of varying density. Most of these smoothed out over time, but a few might have persisted as isolated overdensities, becoming seeds for lone galaxies in an otherwise empty expanse. It's a cosmic roll of the dice where a few players started the game with a completely different set of rules. The implications are profound. If early galaxies could form in isolation, it means the universe's structure is far more diverse than we imagined. Voids aren't just barren wastelands, they might hide enigmatic giants, relics of a time when the cosmos experimented with alternate paths to creation. Future observations could reveal whether these loners are rare flukes or the tip of an invisible iceberg, hinting at entire populations of galaxies that slipped through the cracks of our models. What makes this mystery so urgent is its connection to the universe's greatest unanswered questions. Dark matter's nature, the validity of modified gravity, even the seeds of cosmic inflation, all might leave their fingerprints on these isolated anomalies. Every solitary galaxy is a test case, a laboratory for physics operating under extreme conditions. And as telescopes peer deeper into the void, we're left wondering, are these galaxies cosmic accidents, or are they evidence of a universe far stranger and far less uniform than we ever dared to dream? Stretching across the cosmos like invisible scars from the universe's violent birth, cosmic strings remain one of the most tantalizing what-ifs of theoretical physics. These hypothetical defects in space-time, no wider than a proton yet denser than a mountain range, are thought to have formed during the Big Bang's chaotic cooling, when the very fabric of reality underwent phase transitions akin to cracks forming in freezing ice. If they exist, these cosmic filaments would wield unimaginable gravitational power, warping space around them so dramatically that a single string passing through our solar system could alter planetary orbits in an instant. And here's where the cosmic dawn enters the picture. These strings might have left behind ghostly fingerprints on the universe's first light, distortions so subtle we're only now learning how to look for them. Picture spacetime not as a smooth sheet, but as a tapestry woven with flaws, threads under tension so extreme that they vibrate at near light speed, snapping and recoiling like broken guitar strings. Each oscillation would unleash bursts of gravitational waves, ripples that could have jostled the hydrogen fog of the cosmic dawn, creating faint density variations in the gas. These variations wouldn't just be random noise, they'd form telltale linear patterns like celestial fault lines etched across the sky. The James Webb Space Telescope might have already glimpsed their handiwork, strange filamentary structures in early galaxy distributions that defy conventional clustering models, as if an invisible comb had raked through the universe's first structures. But the smoking gun could lie in the cosmic microwave background. Just as a spider's web reveals itself through morning dew, cosmic strings would leave imprints on this afterglow's sharp, step-like temperature jumps called kinks, where spacetime itself bends abruptly. These signatures would differ unmistakably from the gentle fluctuations caused by quantum noise during inflation. Hunting for them is like searching for a single razor blade in a snowy field, but missions like the upcoming Lightbird satellite are tuning their instruments to the task. Even more provocatively, certain repeating fast radio bursts, those enigmatic cosmic flashes, show timing irregularities that some theorists argue could be caused by strings slicing through intervening space, briefly altering the path length of the signals. The wildest possibility, cosmic strings might still be out there, humming in the dark. Unlike black holes or dark matter, these relics wouldn't dissipate over time. They'd persist indefinitely, drifting through the cosmos like frozen lightning bolts. If one passed near Earth today, its gravitational lensing effect could create duplicate images of distant quasars or distort time itself in measurable ways. Laboratories are already monitoring pulsar timing arrays for the telltale hiccups that would betray a string's passage. What makes this mystery so electrifying is its dual nature. Cosmic strings straddle the line between particle physics and cosmology, offering a potential bridge between quantum mechanics and general relativity. Their discovery wouldn't just solve a cosmic dawn puzzle, it would validate theories of grand unification and illuminate the universe's very first moments. And if they're not real, their absence would force us to reconsider how symmetry broke in the infant cosmos, closing one door while opening others. Either way, the shadow of cosmic strings reminds us that the universe's earliest scars might still be visible if we know where to look. The cosmic dawn didn't just fade into the background of the universe, it transformed. Its once brilliant structures reshaped by time into the galaxies, stars, and black holes we recognize today. But tracing that metamorphosis is like reconstructing a firework from its ashes. The first stars, those colossal population 3 giants, burned fast and died young, their explosions seeding the cosmos with the heavy elements that would later forge planets and life. Yet their remnants didn't just vanish. Some collapsed into black holes, silent and invisible, while others scattered their guts across interstellar space, fueling future generations of stars. The galaxies they called home faced even stranger fates. Many merged, drawn together by gravity's relentless pull, their collisions triggering bursts of star formation that lit up the early universe like cosmic fireworks. Others, too small or fragile, were ripped apart by tidal forces, their stars stolen by larger neighbors, their dark matter halos dissolving into the void. Then there are the black holes, those enigmatic anchors of the cosmic dawn. The supermassive ones didn't just linger, they grew, gorging on gas, dust, and even other black holes to become the monsters we see at the hearts of galaxies today. But the smaller ones, the intermediate mass black holes that should have bridged the gap between stellar and supermassive, seem to have vanished without a trace. Did they merge, get ejected into intergalactic space, or simply fade into obscurity? Their absence is a gap in the universe's family album, a missing generation in the black hole lineage. The most enduring legacy, though, might be written in the universe's very structure. Those early protoclusters, the bustling metropolises of the cosmic dawn, didn't just dissipate, they evolved into the galaxy superclusters we see today, their gravitational pull shaping the cosmic web into the vast filaments and voids we now map. The gas clouds that once glowed with the light of the first stars cooled and condensed, recycling themselves into new stellar nurseries. Even the cosmic infrared background, that ghostly glow we can't quite explain, might be the echo of countless early galaxies too faint to see individually, their combined light stretched and reddened by time. Yet some mysteries refuse to fade. The Lyman-Alpha blobs, those enormous glowing clouds, might still linger in modified forms, their gas now part of modern galaxy halos or stretched into the tendrils of the intergalactic medium. The primordial black holes, if they ever existed, could be drifting unseen through the cosmos, their gravity subtly bending light or occasionally flaring up as they collide. And the first planets, those hypothetical worlds forged in the chaos of the early universe, might still orbit dead stars or float freely in the dark, frozen relics of a time when the cosmos was still learning how to build. The cosmic dawn wasn't an ending, it was a beginning. Every star we see, every galaxy we study, carries traces of that primordial era. The universe didn't just move on, it built itself anew, layer upon layer, with the cosmic dawn as its foundation. And as we peer deeper into space, we're not just looking back in time, we're piecing together the biography of everything, one ancient clue at a time. As we stand at the edge of this cosmic detective story, the 25 mysteries of the cosmic dawn era aren't just gaps in our knowledge, they're portals to a deeper understanding of everything. From the vanishing acts of the first stars to the ghostly fingerprints of dark matter, from the impossible speed of early supermassive black holes to the eerie silence of the missing dwarf galaxies, each puzzle peels back another layer of the universe's grand narrative. Think about it, those first hyper-fast spinning galaxies challenge our laws of gravity. The unexplained cold spots in the ancient hydrogen fog hint at physics beyond our models. and the primordial black holes lurking in the shadows could redefine dark matter itself. Even the cosmic infrared background, that faint, unresolved glow, whispers secrets about structures we've yet to discover. What makes these mysteries so thrilling isn't just their complexity, it's their interconnectedness. Solve one and you might unlock half a dozen others. Crack the code of how protoclusters assembled so swiftly, and you could rewrite the story of galaxy formation. Decipher the true nature of Lyman-Alpha blobs, and you'll shed light on the universe's greatest alchemical feat, turning hydrogen into the building blocks of life. Every anomaly, every contradiction is a thread in a tapestry that stretches back to the very first moments of existence. This is more than astronomy, it's a revolution waiting to happen. The Cosmic Dawn era forces us to question everything we thought we knew about the universe's infancy. Did dark matter behave differently back then? Were the first stars somehow unlike anything we've imagined? Could primordial cosmic strings or exotic particles have left traces we're only now learning to recognize? The answers won't just fill textbooks, they'll reshape our place in the cosmos. Imagine realizing that the universe's blueprint contains chapters we never knew existed, rules we didn't know to look for, and the tools to uncover these truths are already in our hands. The James Webb Space Telescope peers deeper into the past than ever before. Gravitational wave detectors listen for echoes of ancient collisions. Radio telescopes like the Square Kilometre Array map the faintest whispers of hydrogen from the dawn of time. Each new observation is a brushstroke on a canvas that's still mostly blank, a chance to rewrite the story of how light conquered the dark. So here's the real question: which mystery calls to you? Is it the enigma of the first planets, forged in a universe barely out of its cradle? The riddle of those impossibly cold gas clouds defying thermodynamics? Or the haunting possibility of dark stars burning with the power of annihilation? Whatever sparks your curiosity, remember, the Cosmic Dawn isn't just a chapter in a science book. It's an invitation to explore, to question, and to marvel at how much we've yet to learn. The universe's greatest secrets are still waiting, hidden in the light of its first dawn. And the next breakthrough, it might just come from someone like you, looking up and wondering, what if?